Thank you, Steve. All right. Perfect. As Steve said, my name is Michael Jennings. I'm the platforms team lead at Los Alamos National Lab. That basically means that I'm responsible for the team that's responsible for all of our supercomputer systems. That includes everything from a small 32-node cluster. We have several that are about 1,200 nodes, and then of course Trinity is our flagship machine at almost 20,000 nodes. So Los Alamos National Laboratory is one of the 3 NNSA labs. We are responsible for the safety, security, and effectiveness of the United States nuclear stockpile. We do a lot of other science activities. We work with many of the national labs, including Office of Science Labs, LBL, NERSC, and Oak Ridge, and so on. We also work with other government agencies, Department of Defense, Homeland Security, and so forth, as well as a number of commercial partners. We have been doing high-performance computing for a long time, but especially since 1992, when the Test Ban Treaty was put into effect, we were no longer allowed to blow things up in the Nevada desert for real. So from that point on, we've been blowing things up inside of very large supercomputers. The high-performance computing division at Los Alamos has been doing HPC for longer than HPC existed. We had many firsts in high-performance computing, including the first vector computer, the first transistor-based computer, and our Roadrunner system was the first hybrid supercomputer and the first one ever to reach the petaflop level and break the petaflop barrier. Our current division leader is a guy named Gary Grider. He is the one who invented the latest advance in technology called the burst buffer, which allows us to checkpoint jobs across the entire machine at a rate of over 3 terabytes per second. So I wanted to talk today about some myths around containers. Yesterday, I covered what containers are and our container solution, which is Charlie Cloud. Today, I wanted to talk about some misinformation that's out there, or some confusion that's out there in the HPC industry concerning containers. And the very first one is what containers are. If you ask different people what container means, not everybody's going to give you the same story. So we want to make it clear right from the beginning what the terminology is that we're going to use. So containers fundamentally are processes. A lot of times people will refer to containers as the file system image, that stack of layers of files and directories that you tell Docker you want to run in, or whatever your container solution is. And in reality, containers are the processes themselves that run inside of those file systems. Containers simply use features of the kernel called namespaces and a few other technologies that allow us to lie to our applications, to our processes, and show them something about the host that's not really true. We can manipulate what is seen, as you can see here in the diagram, to the application through the kernel. So the hardware is shared, the kernel is shared, but everything else is contained or virtualized. I should probably point out that I sometimes slip and do the same thing myself and use the term container to refer to what's actually an image, or in the Docker speak, a repository. And so if I slip or you don't understand which one I'm talking about, definitely feel free to ask. And you can interrupt at any time with questions. Next myth, containers are the new chroot. So how many people have been using Unix or Linux for, let's say, more than 5 years? Okay, a few. So have you ever heard of applications that secure themselves using chroot? So what chroot does is a process can call the chroot system call, and it can change what it sees as its own root directory from the real slash to something else. And the theory is that once it does that, it's contained inside of that chroot jail and it can never break out. So you can limit the file system view that it has underneath it. Well, the truth is that doesn't exactly work. There are ways to break out of a chroot jail, and these have often resulted in vulnerabilities in those applications that thought they were safe using chroot. So for many years, we've been trying to figure out the right way, so to speak, to do chroot. We want to do that exact thing. We want to change where our root directory is and limit what certain services or daemon processes have access to. But we want to do it in such a way that it can't be escaped. And so when containers came along, everybody thought, finally, this is the right solution. So that's not exactly true. Again, the system call API for containers are basically 3 system calls. And if you pay attention to that last one, setInS, setInS allows any containerized process with the appropriate privileges to change its namespace to anything it wants, anything it can find. So if you have a privileged process, or if a process can gain privilege in any way, it has the ability to, again, break out of that containerized jail and back out onto the host system. And it's built into the kernel. So you really have to understand what the constraints are and what the risk is in order to really secure your containers. Containers use a set of what are called namespaces, which are a feature of the Linux kernel. The 6 of those namespaces are privileged, which means you have to have certain capabilities, and specifically the capsysadmin capability, in order to create those namespaces. Mount is the first and most obvious one. That's the one where you can present a modified view of the file system mount table, what file systems are mounted and where they're mounted, to that process or set of processes. The PID namespace allows you to get your own view, or the process to get its own view of the process IDs on the system. So when you create a new PID namespace, whatever is spawned into that created namespace is process ID 1, which is traditionally init. Nowadays, it could be systemd, it could be upstart, it could be whatever they come up with next, but init is the process or the binary that the kernel executes after it's done. And that's process ID 1. Process ID 1 is special in that not only does it spawn all of the other processes on the system, but it also has to be capable of keeping an eye on them, reaping their exit codes when they exit, which is called waiting on them, making sure not to leave zombies and so forth. When a new PID namespace is created, the first process in it has that same responsibility. So you can't just make any old process create its own namespace. You have to choose very carefully. The next namespace is the UTS namespace, which stands for Unix Time Sharing Service, which dates back to the very early days of Unix. UTS only gets you 2 things, host name and domain name. And the domain name is not DNS domain name, it's NIS domain name, which, unless you're working on computers from the 90s, you probably have never heard of, or at least don't use anymore. But being able to customize your host name is often used and is highly useful. The network namespace allows you your own view of network functionality. So that gets you not only your own interface and IP address, but an entire TCP/IP stack that is unique to you. So things like IP tables, firewall rules, routing tables that are custom, et cetera. Unfortunately, unless you are a privileged process, the only thing you get access to in a container is a loopback device. So in order to do any actual networking, some privileged process somewhere has to create a MAC VLAN tunnel between the container and the outside world, or something similar to that. IPC namespace just gives you your own view of IPC resources, things like POSIX message queues, System 5 shared memory, and so on. And the last one is a fairly new one. The cgroup namespace gets you your own custom view of the cgroup tree. Using cgroups does not necessitate having a cgroup namespace. So when I refer to cgroups later on, I will not be talking about this namespace. I'll be talking about the functionality itself. And then there's one namespace that any user on the system can create. So it's unprivileged because it doesn't require any special capabilities to do it. And that's the user namespace. When you create a user namespace, if you're root, you then tell the kernel, I want to allocate this range of numeric UIDs and this range of numeric GIDs into my namespace and map them to equivalent ranges on the outside. If you're unprivileged, you get one mapping each, one UID mapping and one GID mapping. Everything else gets mapped to anonymous, unprivileged number, which is 65,534, I believe. It's -2, so depending on if you have 16-bit or 32-bit or 64-bit UIDs and GIDs. That user namespace is primarily what we concern ourselves with, because for the most part, we want to be able to run containers that are unprivileged, that don't have access to access capabilities or system resources, and that's one of the ways that we can secure containers against escape by creating unprivileged user namespaces. There are also a number of other features that typically get coupled in with what we refer to as containers. Docker supports all of these, for example. Other specifically HPC-focused runtimes don't necessarily support all of these, but tend to support at least some of them. So cgroups or control groups allow you to put specific limitations and constraints on processes. So if you wanted to limit a process or a family of processes to some portion of memory or some portion of CPU time, you can do that using cgroups. Setcomp BPF is a filtering mechanism where you can define which system calls a process can or cannot use. So you can specify a system call and then determine if it's allowed. You can say it's denied, and you can write a little program in memory that has all of these things, and at the end you can have a default policy of allow or deny. So it works in whitelist or blacklist mode, so to speak. prctl no new privs is a permanent flag that you can set on a process. It follows through to all the children, and there's no possible way once it's set to change it back to 0. And that flag tells the kernel whenever this process or its children fork off and spawn additional subprocesses, those subprocesses are not allowed to gain any additional access or privileges. So normally when you run a set UID or set GID binary, the exec system call in the kernel assigns the new UID or GID to that process, but this prevents that from happening. If you have one of the privileged container runtimes, meaning that the thing that's launching your containers is run by root, the only safe way to do that is to have that flag. And if you have a kernel that's too old, like the RHEL 5 and earlier kernels that don't have this flag, it's not safe to run any sort of container on those. SE Linux is a very advanced security system. You basically assign labels, assign identities to processes, to files on the file system, and those labels must match both who they are, so to speak, and what they want to do. So you can say when HTTPD gets launched, it has this label, and this label is allowed to do these 3 things only. And anything else it tries to do, the kernel will deny it. Now, it can be a massive pain in the butt to actually get that working, and it's very, very complicated. But it also makes for very safe containers. The vast majority, if not all, of the previous container vulnerabilities that have come up can be prevented by correctly configured SE Linux. If you're more used to the Debian and Ubuntu world, you've probably never used SE Linux because they don't support it. What they do support is something called AppArmor. AppArmor is similar in concept, but completely different in implementation and in complexity. So each application that you want to use with AppArmor gets a configuration, or what's called a profile, and that profile determines what it is or is not allowed to do. So all of these things combined are what we refer to as container capabilities or container features within the kernel. So the next myth, you've probably heard containers are lightweight VMs or more efficient VMs. Or you might have heard that you should use containers to replace your servers or to virtualize your servers. They're like VMs but better. So containers are not VMs. They're not lightweight VMs. They're not any type of VMs. Typically, when we refer to virtualization, we're talking about re-implementing something that used to be hardware in software. So things like memory and processors. When you run a VM, you're actually running software versions of a computer chip and software versions of memory chips. Containers, on the other hand, don't virtualize hardware. They just allow us to lie to our applications and use the features that are already in the kernel. In the Docker world, we refer to them as application containers, specifically because we're trying to take an application and tie the environment that we want it to run in to that application specifically. So if you have a scientific application that has a lot of different dependencies, especially Python scripts, on Debian or Ubuntu, you can pretty much apt-get install any Python script or any library ever written. And so it makes it very easy to install an application very quickly and get it up and running. That's not quite so easy on Red Hat or SUSE, which are the predominant supercomputing platforms that we see in the HPC industry. So containers allow our scientists, our customers, to couple their application with the operating system they want it to run with and all of its libraries and dependencies all into one container and run that contained application on any of our platforms. So they could be Trinity, they could be a supercomputer at Oak Ridge. It no longer matters where it's running because it has all of its stuff inside that container. There are other container systems that don't work the same way as Docker, though. You have almost certainly heard of Docker. You might not have heard of systemd nspawn. Who's heard of systemd nspawn before? All right, that's about what I figured. So systemd is the new boot mechanism. It's so much better than everything that's come before because it wants to own literally everything on your system. It controls logins, it controls processes, it controls devices, it controls everything. And so, of course, they had to have their own container implementation. So systemd nspawn allows you to boot a container, but it's systemd, so systemd has to own that other container. So with nspawn containers, it actually is an entire bootable system image. You're just booting it with systemd nspawn rather than a VM, but it's essentially the same type of concept. There's also something called LXD. If you've been using Docker for any amount of time, you probably remember LXC. LXC was the first container solution that Docker used under the hood. Well, that project, even though Docker abandoned them, has continued working. And the latest versions, LXD, offer you a lot of VM and cloud-like features. So if you set up a whole bunch of machines running LXD, you can migrate containers between machines live, you can snapshot, you can do all the things with containers that VMware, vSphere, and libvirt allow you to do with virtual machines. But we're specifically going to look at application containers. So if you've ever been to other container talks, specifically container talks by security guys, you've probably heard them say containers don't contain. You've probably heard other people say that containers do contain. I mean, they're called containers after all. So what is the truth? Well, in reality, they're both right and they're both wrong. So containers, when we talk about containing applications or containing processes, we're not talking about building a fence around them or putting them in jail. The containment that we're referring to is more of a grouping, like a bucket or a Ziploc bag. It's a way of tying one or more things, processes, applications, libraries, all of that stuff, tying things together in a group and then doing things with that grouping that limit what they can do, what access to hardware they have, and so forth. So containers do contain, but they contain passively, not actively. And if you launch a container with privilege, that container will be able to, if it knows that it's contained, move out of that containment. So unless you are running unprivileged containers, meaning that you're spawning them as a normal user, then you're not fencing them in any way. Does that make sense? Okay. Next myth. Container is shorthand for Docker container. So for quite a while, this was actually true. Nobody was paying attention to any other container technology than Docker. Docker took off like a rocket, especially in the web app industry, because it made deploying web apps and the services that they relied on simple and easy and very, very fast. So Docker facilitated a lot of agility in the web app world, the places like Google and Amazon and Facebook and so forth. So they rely on container technologies to be able to deploy and manage humongous web apps all across systems throughout the world. And Docker knew that they were the only solution in town that anyone was actually using. And so they didn't really care what anyone else said. If it didn't match up with Solomon Hykes' vision, who is the original author of Docker, he just said, you know, you're welcome to go off and write a patch or a module, but we're not going to mess with that. That was the answer we got when we asked about HPC solutions, and that was the answer that very important people in the industry got, like the guys behind CoreOS, when they asked about signatures and content assurance and those types of things that Docker wasn't doing. So it was very, very easy to take a Docker container, manipulate the content, keep the same hash, and cause people to download bogus or even malicious containers, because Docker didn't do anything about validating unchanged content back then. And so since Docker Inc. wouldn't listen to the people who were asking them for these security features, they decided to go off and create their own solution to the problem, something called Rocket. So CoreOS came out with Rocket. They also came out with a very lengthy manifesto about the dangers of letting Docker run rampant across the industry and do whatever the hell they wanted and not listen to anyone. When this happened, it looked very strongly like the container community was going to fork. It was going to split in two, and some people were going to go the Docker way, some people were going to go the Rocket way, and that was not going to be good for anyone. So some of the larger, more powerful entities in the container world, people like Google and IBM and Red Hat, started banding together, and they formed a coalition against allowing that to happen. So they created what was called the Open Container Initiative. The Open Container Initiative is an independent standards body run by the Linux Foundation, where all of the powerhouses in the container world, so to speak, have a committee that controls the standards for containers, both the container images and the runtimes. Well, Docker saw the writing on the wall, and they didn't want to be left behind or let this challenge go unanswered, but rather than fighting back per se, they figured it was better to generously contribute their current implementations as the reference standards for the official first version of OCI containers. So all of a sudden, Docker's runtime and Docker's container format became the OCI runtime and the OCI format. And Docker went and split their stuff apart in order to make that work. On the other side of the house, those of us in the HPC world were trying to get capabilities into the existing container engines to work the way we needed them to. Long story short, the only real solution that was safe at the time was an authorization plugin for Docker that would limit access to the Docker API. And Docker Inc., in their infinite wisdom, decided to make that an enterprise edition only feature. So suddenly we no longer had an option for plugging into Docker even to limit access, let alone address any of the performance or usability problems. So we knew we had to go our own way. The first one was Shifter. Shifter is a project started at NERSC, just across the bay. And what they decided was they wanted to optimize the user experience. So users of Shifter, all they have to do is add one single line to their script, their job script, where they submit to Slurm or Moab or whichever scheduler they're using. And they say, I want to run my container in this, or I want to run my job, in this Docker container. Done. As long as that Docker container had been pulled down from Docker Hub and was stored locally, it would just work. The administrator, however, had a lot more work that they had to do to set Shifter up. They had to allocate a system to be the image gateway. They had to have parallel storage to distribute the imported image that got downloaded from Hub and so forth. So there was a lot of overhead. And because they wanted to support older kernels, older operating systems that didn't necessarily have user namespaces yet, they use a setuid root launching mechanism, which adds security implications. Lanel, about the same time, started the Charlie Cloud project. It was originally intended to be something to manage virtual machines, to manage a cluster in a cloud-like way. When the container things started taking off, they pivoted and turned it into a lightweight container solution. So now, Charlie Cloud allows you to launch unprivileged containers using user namespaces on any system that is modern enough to support the user namespace combination. That includes most any distribution that's in common use today. RHEL 7, SUSE 12 SP2 and later, SUSE 15, and of course Debian and Ubuntu have supported it for quite some time already. Now both of these projects had the same perspective. We didn't want to go and re-implement the entire gamut of container software and technology, because then you'd have to have your own registry server, you'd have to have your own prescriptive method for building containers, you'd have to reinvent the wheel. Docker's standards and OCI's standards were perfectly capable of handling everything right up until you get to the point of running on an HPC system. That's where it falls apart for a few different reasons, one of them being that the overlay FS, the way it layers container images one on top of the other, is very, very slow for file system access. And the other being because the Docker daemon runs as root. And until recently, there was no other way to do it. So both of those projects only wanted to implement a runtime. For everything else, like building containers and moving containers around and storing containers in a registry, for all of that, you just used the Docker stuff because it worked and it was fine. A different project, on the other hand, took the complete opposite approach. Singularity decided that Docker sucked and OCI sucked and everything sucked, and they had to rewrite all of the different things that made up the container ecosystem with proprietary, incompatible code. And so that's what they did. And the first version of Singularity wasn't even a container solution. What it did was it would watch your application, your process, as it ran, and it would run it under something called strace, which shows you all the system calls that the application is executing. And they looked through the log file, searching for calls to open, the open system call. So you're opening a file somewhere. So they gathered up all of these files that your application opened as it ran. And when your application finished, it took that list of open files and made a CPIO archive, which is kind of like a tarball, out of those files. And that was your so-called container. And then when you ran it later as a containerized application, it would simply go into temp or var temp, unarchive that CPIO archive, chroot your application into it using chroot, as I mentioned earlier, and then intentionally break out of that chroot jail back to wherever you launched it from. So when your application would try to open a file, if the path you gave it started with a slash, it would open that file from inside the container. If it didn't start with a slash, it would open from wherever you started it, so your home directory or your scratch directory or whatever. So that was how they faked being a container, except they didn't actually tell anybody that this is what was happening. If you can picture this in your mind, you can imagine how well this went. So within literally a matter of weeks, Singularity 2.0 came out, and it was a complete rewrite. It actually did use namespaces, but it used them incorrectly. So on the one hand, you have Singularity, which is completely incompatible with everything that works out, that's already out there in the ecosystem. And then you have Charlie Cloud and Shifter, which were both only runtimes, and they took very distinct approaches to how the runtime should enable unprivileged users to run containers. And then we have these otters over here. So these otters are the Red Hat project called PodMan. PodMan is fairly new, and it's not specifically intended for HPC. The guy I mentioned earlier, Dan Walsh at Red Hat, he's their SE Linux guru. He's also a security guy, and he hates with a passion the idea of running containers underneath a root daemon. So the PodMan project re-implemented literally every single thing that Docker can do, but they re-implemented it without the daemon. You can literally install PodMan on your machine, you can alias Docker equal PodMan, and you can continue to run all of your same Docker commands that you've been running all along, and they will continue to work exactly as they did before, only you're running PodMan instead. And there's no root daemon. They also recently fixed unprivileged building and unprivileged containers. So unprivileged containers are now fully supported under PodMan. They only made one little goof. The newer versions of Fedora come with some setuid helper commands called new UID map and new GID map. You remember I talked about those ranges of UIDs and GIDs if you're running a privileged container? Well, these set UID root binaries allowed unprivileged users to allocate those UID and GID ranges. Unfortunately for us, that doesn't fly. We couldn't allow these set UID processes to be part of our secure classified container build process. And we can't just bring in containers from the outside. So we were stuck. We took apart the build code, tried to figure out what was going on. We found the place where it was breaking, and we wrote a patch to re-enable unprivileged container builds in Builda and PodMan to function correctly without any set UID or set GID helpers. We've sent the patch upstream to PodMan, or to Dan and his team. They have looked at it. They say they are willing to apply it. I don't know exactly which version it will be in, but it should be in soon. So we will have a fully unprivileged build mechanism through PodMan and Builda very, very soon. So next myth. Containers are complex and you have to have some big program like Docker or Rocket to manage your containers. So containers themselves are actually pretty simple. You remember earlier I said there's 3 system calls that make up the entire API for dealing with containers. It's pretty simple. And in fact, in all modern operating systems, RHEL 7, RHEL 8, current SUSE, all of them come with new enough versions of a package called util Linux. Everybody heard of util Linux? It's a gathering, as the name implies, of utilities for Linux. So the new versions of that come with 2 commands that account for all 3 of those system calls. So thanks to those 2 commands, it's now very simple and easy to write your own container solution using bash, using nothing but shell commands. And I've actually done this. We run a piece of security software for scanning our machines and making sure that they are up to date, don't have vulnerabilities, and so forth. The problem is, this particular application, the centralized server sends commands to the agent to run. And it can literally run anything. We didn't like that for HPC. And for longer than I've even been at LANL, we always told the security group, no, you can't run that on our system. If you're familiar with clustering, you've probably heard of parallel file systems like Lustre or GPFS. Imagine what would happen to your metadata server if you had a Nessus the agent run basically a find, a metadata query across your entire file system. Now imagine that you did that on every node in a cluster and every cluster in an entire data center. Your file system would fall over. It would die. And it would die before any one of them could even get anywhere near completing. So we couldn't allow the risk of letting the agent just trample over all of our file systems. So we couldn't run it. Well, the topic came up again, and I suggested, well, why don't we just containerize it? Nobody believed me, so I said I would do it. And so I wrote a little shell script that could be launched by systemd or upstart or whatever your init process is, and unmount all of the file systems that it doesn't need, mount root read-only, and the only thing that would stay writable was the daemons directory and a little /temp ramfs for scratch space. And then it would spawn the agent. The agent would run. It could still see the root file system. It could still query the RPM database, and it could still look at what the settings were and what the versions of everything were, and it could do whatever it needed to its heart's content. unless it tried to do something malicious. And then it would not be able to write to the file system. We've now successfully deployed the solution across all of our clusters, and they're all now running our security software for the first time ever with one shell script. So containers are powerful, and they're really not that difficult. But I cheated. I used commands that already existed to manage the namespaces. And that's all you would really need to do. If you try to engineer your own container implementation, that's where things get really complicated really fast. There are lots of little nuances and weird corner cases that can happen with containers that aren't necessarily well documented. A lot of them we, the Charlie Cloud team, have had to run into and troubleshoot and figure out on our own. And none of us is a kernel developer. So it took us a while to get it. And in fact, we tried to document all of the ones that we could in the examples directory inside of the Charlie Cloud source tarball, because there's a lot of them. If you don't have to reinvent the wheel, don't. There's already lots of stuff out there for doing containers the right way or the easy way, depending on how you look at it. And I highly recommend using those, especially if you're not quite sure how to get it right. Using Bash is really easy. Systemd also supports spawning services inside of different namespaces on its own. So you can actually use systemd configuration directives to launch containerized services really easily. This is probably my favorite myth of all. Docker is insecure. How many people have worked a lot with containers before, just out of curiosity? Okay, not very many. Of those, how many of you have heard somebody tell you that Docker is insecure before? Same people, okay. And well, actually, Docker's security record isn't very good. I went back and I counted from 2017, which was the point at which all of the runtimes that I mentioned earlier actually existed. Since then, there have been 18 different vulnerabilities that came up, and the majority of them have been root compromises or information leaks of various types. So pretty serious stuff. In all of that time, with all of those vulnerabilities, they only got 3 CVEs. And that's only been recently. Before that, they apparently didn't care about getting security identifiers for vulnerabilities. And one of those CVEs that they did get covers several different vulnerabilities that would allow you to overwrite stuff in user bin. So you could replace any of the commands on the system with whatever you wanted, surreptitiously. And so anybody, even root, would then be executing your custom commands rather than the operating system commands. There were 9 releases altogether last year, calendar year 2018. Of those 9 releases, 7 of them were to fix security vulnerabilities. 7 out of 9. So when one of the security experts for one of the major distributions went to evaluate for inclusion into the operating system, they said a lot of, well, let's just say not entirely friendly things about the software. The code for the setuid stuff that ran as root was very difficult to read. It was difficult to tell if it was being called by privileged code or unprivileged code, which probably resulted in several of the vulnerabilities. And the assessment was this code should only be in the distribution if only a particular group of users is allowed to run it. So create a Unix group, make it only executable by that Unix group. Otherwise, he strongly recommended not including it into the operating system at all. So of you who have been working with containers, how many knew that Docker was that insecure before? Had that many problems? Nobody. Well, there's a reason for that. None of this is actually true about Docker. It's actually true about Singularity. So the facts about security and container implementations for HPC. Docker has had a few, granted, depending on how you count, somewhere between 2 and 5. But what you have to remember about Docker, and what people often forget when they claim that Docker is insecure, the default installation of Docker is only accessible by root. Period. Unless you already have privileged access to a system, you cannot get to Docker. You can't tell it to do anything. So it was not designed to be open to any user on the system. Just because you can do things with access to the Docker API that will get you root, that's by design, because it was never designed to be accessible by anyone. It was only supposed to be accessible by trusted users. So really, are those vulnerabilities security risks in Docker? I would argue no. The only things that would be a vulnerability in something like Docker would be if Docker allowed a malicious container downloaded from the internet to compromise your system. So that's why it's somewhere between 2 and 5. Charlie Cloud, I'm proud to say 0. No security vulnerabilities. Well, and why is that? We don't run privileged. When you run Charlie Cloud, you're running as yourself. You don't have any additional access. And you are limited to exactly what the kernel of the system allows you to do. So if there's a vulnerability in the kernel, sure, you might be able to increase your access. But if there's a vulnerability in the kernel, that's already true, because that's your point of trust. You are trusting the security boundaries laid out inside of the Linux kernel to keep your system safe. If the kernel developers screw up, you're already in trouble. And so with Charlie Cloud, or with user namespaces in general, you're not adding any additional trust. On the other side, if you have a setuid root wrapper or setuid root executable as part of the container launching mechanism, not only are you trusting the kernel to get it right, but you're also trusting those programmers who wrote those setuid executables. You're trusting them to have gotten it right too. So keep that in mind when you choose a container solution. And I like that tagline up there. If you open up access to the Docker daemon to users on your system, Docker is not the vulnerability, you are. Next myth. Containers or specific runtimes for containers solve the problem of reproducibility in science. You've probably heard of people talking about containers for reproducibility. How do I take my application that I've just run my science in, how do I preserve that for all time so that somebody in the future can take my program and reproduce my results? Oh, containers, that'll solve everything. Well, no, not exactly. Containers solve a problem of reproducibility, or more specifically, if you build a container using a Docker file or some sort of prescriptive method for creating that container, then somebody later on can go and use those same mechanisms to reproduce your container. But that doesn't solve the problem of reproducibility in science, or having somebody reproduce your results later on. Why? Because in the vast majority of cases, we don't tie our container creation or our software builds to specific points in time. We want to automatically use the latest and greatest version of whatever's out there. And so there's no way for you to guarantee that the instructions that are executed in your Docker file or any other config management solution, that the results of those instructions will be exactly the same even next week that they are today, let alone 5, 10, 20 years from now. If you say yum install some package or apt-get install some package, you're going to get the latest of everything that may or may not be compatible, may or may not work, might not even be in the repository anymore. Or when you say from some particular container tag, you're basing your container on somebody else's work that may have changed. And in fact, more often than not, when you Docker run a container, it's going to go off and say, oh, I need to pull down the latest version of CentOS 7 because there's a new one on the Docker Hub. So reproducibility is partly addressed by containers, but we have a lot more work to do to really and truly make these things persistent. And it starts with having some place to store all of these artifacts forever and ever and all time. And we just don't have that today. And there's also issues with the tar format that make this essentially impossible, so we'd have to fix tar too. One of the container runtimes has a slogan that says, our solution is secure because your UID inside the container matches your UID outside the container. Therefore, it must be secure. If I told you to go on your Linux box and take bin bash and make it setuid root, would you do it? After all, if you run bash and it's setuid root, when it runs, you'll have the same UID inside that you had outside. So it's perfectly safe, right? So would you do it? Well, of course not, because there's a whole lot of stuff that goes on between the time you run bash and the time you get your prompt. And somewhere along the line, you have significant opportunity for something to go wrong. And it's the same with containers. Just because you have the same UID inside and outside doesn't necessarily mean you're safe. You have to understand the security boundary that you've accepted, because that's your risk profile. When you do a risk analysis, you have to know where your risk is coming from. On the one hand, it's the kernel and nothing else. On the other hand, it's the kernel and a whole bunch of third-party software. Privileged operations are privileged for a reason. And a great deal of thought has gone into putting the right stuff in the kernel to make sure these things are safe. And the things that aren't safe are restricted to only privileged users. So if you're going to second guess all of that thought from all of those kernel developers, you're taking a significant risk, and you really need to know what you're talking about and what you're doing. So override their thought process at your own peril. User namespaces are too new to be considered secure. So actually, they've been around for a surprisingly long time. It's just that nobody was talking about them for a while because they weren't very well known. And most people who were assuming that Docker was equivalent to container only knew the Docker implementation of user namespaces. And when you use user namespaces in Docker, you get the privileged version. And that's not particularly useful. But user namespaces have been around for the majority of this decade. They were feature complete back in 2013, so all of the code was in to make them do what they were intended to do. There were a few vulnerabilities found in the very beginning, but they've been substantially consistent since 2015, so that's almost 5 years now. And the container solutions which use unprivileged user namespaces have actually protected users against all of the most recent vulnerabilities. And all of the current distributions support them. So unless you have a very old operating system or have to run under a very old kernel, you should be in good shape. So I've mentioned Charlie Cloud several times throughout the talk. It's available for free on GitHub in HPC/Charlie Cloud. We just, literally like last week, released 0.10. And this new release is a game changer in my opinion. So one of the things it offers is a brand new command called chgrow. Why he called it chgrow, I really don't understand, but he did. It's really the builder. So we now have a command which can interpret Docker files on its own and build containers completely unprivileged. Now there's a couple caveats to that. It does not currently implement all of the Dockerfile vocabulary that Docker supports. It has all of the most commonly used stuff in it, but there are a few keywords that are still missing. And it also requires two commands that are external, Yumoki and Spokeo. They're both supplied with RHEL 8 and Debian and Ubuntu, but there is no CentOS 8 yet. There's still CentOS 7, and CentOS 7 does not have those commands. I was able to find an RPM for Yumoki for CentOS 7, but not for Spokeo. If you're a Go developer and you have your own Go environment, you can already build Spokeo yourself for CentOS 7 or RHEL 7, and it'll work just fine. Stay. But there's no easy place to go and just download it and install it. So for that, we're just going to have to wait a little bit until CentOS 8 comes out. But if most of you probably use Ubuntu, so you should be good to go. It also has the patch. I mentioned that there are those two setuid wrappers that are in the Builda code. It comes with a patch for Builda to remove those. It's the same patch that we sent upstream that's going to be in the future version. But for now, you can apply it yourself and rebuild Builda, and everything will just work. We also have a series of new wrapper scripts. Charlie Cloud is what we call workflow agnostic. Basically, we don't care how you get the root file system image. You can build it with Docker. You can build it with yum-install root. You can tar it up from an existing system. It doesn't matter how it comes into being, as long as you get a tarball that looks like a root file system. That's all that really matters. However, there are certain workflows that are more common in the HPC world and have certain advantages for us and for our customers, the scientists that we serve, and make more sense for our systems. So we have the system Trinity, which has almost 20,000 compute nodes. And if you untar a tarball into a parallel file system that's large, and you try to have 20,000 nodes access that tarball's contents all at the same time, it will not perform well. Anybody know why? I said it earlier. Metadata. All of the querying and finding of dependencies and data files and such all generate queries for metadata to the metadata server. If you do an ls, you get a bunch of file names. All that is what's called getDents, which is get directory entries in the kernel. If you do ls-l, you get all of the information. You get permissions, you get link count, you get file type, etc. And the difference is for every single one of those directory entries that getDents returns, it has to go into a stat. And stat queries the metadata server to get all that information. And if you have 20,000 nodes doing that all at the same time, it's going to slow to a crawl and possibly crash. That's where SquashFS comes in. You can, if you're not familiar with it, think of it kind of like a tarball or a zip file that you can mount as if it were a file system. So it's compressed. It takes up less space than normal, just like a tar.gz file or whatever. But you can mount it like a file system, just like a CD-ROM or a hard drive, and access everything in it. But now your metadata query to your metadata server is only done one time for the SquashFS file itself. All of the other metadata is actually inside the SquashFS file. So SquashFS is a huge win for high-performance computing. That's why this workflow matters so much to us. And so using SquashFuse, which is a user-mountable, a userland driver to mount Squash file systems, we can now provide several additional commands for that workflow so that you can very easily deploy SquashFS files instead of tar.gz files. So all that's new with the 0.10 version. Those of you using OpenHPC, they have not quite caught up yet, so you'll need to download and build it on your own. But if you have any problems, we're happy to help. You can file support issues at GitHub. And if you'd like to contribute, we also accept pull requests there as well. And we've now been added to OpenSUSE as well as NixOS. We've done a lot of press, so to speak, on Charlie Cloud. So if you'd like to hear more about it or read more about it, the inaugural publication was a Supercomputing 2017 paper that was written by Reed, who's the primary author, and our colleague Tim. That's probably the original definitive source, but of course we've changed a lot since then. There was also a login article in the Usenix magazine login. We've got lots of great documentation in read the docs format. Obviously the source code is on GitHub. We also have 2 mailing lists at groups.io that we invite you to participate in. And you can contact any of us if you like. So we hope you try it out and see how you like it. And I'd be happy to take questions.